Okay, we reached 50 participants, so I guess it's working. I'll start by explaining a bit about Clowder. Welcome to the second day of CPP. Apparently things are working a bit better. The sponsors have rooms, and I wanted to show you how you get to them. Let me see 1 second. Can you see my Clowder window?
Yes.
Okay. So as usual, you have the Clowder chat where you can ask your questions. Since today, our sponsors have their logos and names in the sidebar, and you can go to their room if you want to talk to them. And one thing I wanted to mention is that, yeah, 2 of the CPP sponsors are not tagged as such, JetBrains and Galois, because they're also Popl sponsors. But I don't think, I hope that's not a big problem. Other things I wanted to show you is that there's an information desk where you can ask questions, and hopefully you'll get answers. And yeah, while some of the problems seem to be fixed today in Clowder, one thing I noticed is that if I hang around on a chat for a few hours, the round trip time for messages in the chat becomes more than a minute for me. And if I refresh the window, it becomes 3 seconds again. So if you're having round trip time problems, you can try that. Okay, so I'll leave it to Andrei to introduce the invited speaker.
All right. So, Katalin, you can hear me, right?
Yes.
Hello and welcome from me as well to the second day of CPP. It is my great pleasure to introduce our invited speaker, Peter Sewell. Peter has been a professor at Cambridge since 2012. He is, of course, well known in our community for his impressive specification and verification work on the semantics of real-world hardware and software systems. If I am to describe the spirit of his work in 3 words, I would say, yes, we can. Over the years, his research covered a wide range of topics, such as security enhanced hardware, relaxed memory concurrency, rigorous semantics of the C language, internet protocol specification, distributed access control policies, types of distributed languages, process calculi, and many others. Today, we will hear about an exciting journey of underpinning the foundations of existing hardware architectures using formalisms and tools developed by Peter and his research group, also in collaboration with other groups within the high-profile project Cherry. Peter, please.
Okay, thank you very much for that introduction, and you and Katalin for the invitation to be here, and also to everyone in the audience. Thanks for coming along. So, let me have some slides. So as Andrei said, this is joint work with actually quite a lot of people, and I won't read out all their names now, but I'll highlight some of the main ones now. But this is a great gang of people from several different overlapping projects. That's why there are so many of them. Let me also, before I really begin, highlight that we're actually hiring at the moment for further future postdocs and research engineers. So if you're interested in that, or you know someone that is, please get them to contact me actually in the next couple of days, because technically the deadline might have already passed, but I think we may still be able to wrangle one in. So underpinning the foundations, what do I mean by that? So we talk a lot in this community about the foundations of computer science and discrete maths and logic and semantics and lambda calculus and types and so on, all good stuff, like motherhood and apple pie for many of us. We talk less often about the actual foundations of computing as it is practiced out there in the world. So all these things, there's different layers of abstraction that we work with, from silicon to RTL to architectures to these fine languages of JavaScript and PHP and what have you, up to operating systems and beyond to sort of data center computation. And these are the foundations above which the industry builds beautiful, elaborate constructions with elegant user interfaces and finely considered design. And it is, as we know all too well, constantly on the point of falling over. All right? So these foundations, very regrettably, have not sufficed to build things that do not fall over or are not on the point of falling over. And we very rarely consider all of these things when we're building these things. So if you're in the unfortunate situation of having spent, lots of effort and vast amounts of money constructing an elegant building on top of dubious foundations, then what do you have to do? So there is this process, a horrifying process for building owners, but maybe a good process for construction engineers, of underpinning, right? The process of strengthening the foundation of an existing construction. And that might be necessary for various reasons, all of which apply in this analogy to us. So the original foundation isn't strong or stable enough. The usage of the structure has changed, and the environment supporting the foundation has changed. So all of these have happened to computing since these practical foundations, these things, started being developed in really the 60s and 70s. A lot of what we have still dates back to that. So how can we possibly, given all of the investment in construction above these quite dubious foundations, how we can establish something better, something more trustworthy? And how can we do that for the systems that we actually depend on, all of your telephones and operating systems and what have you, not the ideal systems that we might, as semantics and verification people, like to have? And let me ask, moreover, how can we do this for these full-scale systems with all the complexities that they embody? So that's both fundamental complexities, real reasons why they are subtle and complicated, and also the contingent reasons, the accumulations of historical accident and layers upon layers of stuff. Yeah. So we're going to talk about that today with the aim of supporting more rigorous engineering, not necessarily full verification all the time, but verification which is, engineering which is informed by and uses rigorous semantics, maybe in some lightweight way, or maybe in some cases for full verification. If we're going to do any verification, at some point we have to make the shift from the physical non-mathematical world to the formal mathematical world. Right? We have to construct a mathematical model on which to stand. And sometimes we will just posit that out of thin air. The best we can do is at least to empirically validate that our mathematical model does reflect reality with some confidence. And then above that, we can do analysis or proof or what have you. So we could do this, we could take this shift from the informal to the formal, from physical reality to mathematical space. We could make that shift at any point in the stack of abstractions that we work on, right? From silicon up to operating systems or data centers or what have you. In this talk, I'm going to focus on the architectural layer, right? The interfaces defined by ARM, Intel and AMD, RISC-V International, IBM, and so on, that define what we can rely on from the processors, and conversely, what the processor implementation teams have to produce. And that's not forced, right? We can perfectly well just ab initio start looking at C, or if we were very strong, Perl, and try and understand what its semantics is in its own terms. But this architectural layer has a lot of advantages. It's very attractive from a verification point of view. So one is that the hardware is kind of reliable. It's certainly not perfectly reliable, but hardware vendors do quite extensive validation that the silicon they produce does implement the architecture spec. So the architecture spec is quite a meaningful entity in that sense. The architecture is also, while they're usually rather large, conceptually rather simple compared with high-level languages and operating systems. And this means, or the combination of these two things mean it's easier at this architectural level to get confidence that any verification we might do relates to what's actually running on the binary and how it behaves. So there are going to be two parts to this talk. So one, I'll talk a bit about production architecture as it is now, focusing especially on ARM v8, the A-class architecture, which is the one used in your mobile phones and tablets and so on. They also have a microcontroller architecture, which we'll not talk about today. And then the second part of the talk, we'll talk about production architecture as maybe it might be in the future, maybe as it should be, about these cherry extensions that Andre mentioned. Now, I should say, so this is like a longer talk, and we can, if you all choose, make it quite interactive, right? So if people want to ask questions as we go through or interrupt me, then post something up in, let's say, the Clouder discussion room, and I will try and pay attention, or the chairs can interrupt me to make me pay attention. And maybe I'll pause at some point or other to encourage that further. Okay, so production architecture as it is now. So the traditional practice is for the architecture vendors, ARM, Intel, what have you, to write books. And these are very large books these days, right? So ARM, this nice RISC architecture, has a book which is a mere 8,248 pages long. And historically, the architectural spec has not been altogether well defined, especially for concurrency stuff, which we'll get back to later a little bit, but even for the instruction behavior, right? So historically, these books have been purely prose and pseudocode. So because they're not, I mean, they're certainly not mechanized in the prover, but they haven't been mechanized as any kind of artifact. And that means that they are really literally books. They have been usable as documentation, but not directly for any testing or analysis or proof or any computational thing, because they have not been computational artifacts. So the first thing that we can do about this then is to look at that. And let's look first just at the sequential aspect of that. Right? So the sequential behavior of instructions, which includes decode and address translation and all that kind of stuff. As I said, these have historically been pseudocode. Over the last few years, middle of the last decade, ARM transitioned internally to a mechanized language, and that was led by Alistair Reid and his colleagues. And what we have done since then, we reported on this in our Popple paper in 2019, is automatically translate that vendor specification into a domain-specific language that we've produced, SAIL, which has been custom designed to support architecture specification. So it's intentionally a small and simple language, imperative first-order language. There's a bit of subtlety in the dependent type system for bit vectors, which Alistair Armstrong and Mark Wassel and Neil Krishna Swami have been working on. Mark will give a, what is it? I think it's a lightning talk later today, which will touch on some of that. Other than that, SAIL has very simple semantics. It's very inexpressive, which makes it good for analysis. And it's an open source thing. And from that SAIL architecture specification, actually for any of these architectures in this picture at the top, we can generate automatically a bunch of useful artifacts. We can generate C emulators for testing. We can generate theorem prover definitions for Koch and Isabel and Hall 4 for verification. We generate SMT definitions actually in a couple of styles, and we can glue those or basically the architecture spec itself into tools for evaluating the concurrency behavior. And all of these are available and available for you or other people to use in verification. We would love for people to be doing that. Right? So focusing in on this ARM model then, so this is the full sequential ISA. It includes floating point, address translation, exceptions, hypervisor modes, crypto instructions, vector instructions, pointer authentication, all of that stuff. And that kind of authoritative and complete ISA description has not previously been publicly available for formal reasoning. Is it something you can trust? So it's about 100,000 lines of spec. That's quite large compared to pencil and paper maths or your typical academic paper, but it's quite small compared to a program. But what about the generated definitions? Is it correct? Well, we checked with Alistair Reed, who was then at ARM, against the ARM internal architecture validation suite, and it did a pretty good job, 99-point-something% as compared with the internal model. Is it usable for sequential testing? Well, you can run code in the generated emulator. It's not super fast, but 200 kits, it's enough to boot an OS. Is it usable for proof? So Thomas Bauerreis, just as a sort of a demonstration exercise in that Popple 19 paper, proved the characterization of address translation, which is one of the most subtle aspects. That was in Isabel. Let's look at it in a bit more detail, just to understand why you have 100,000 lines of spec here and what the sort of quality of the definition is. So let's think about an ARM instruction. Let's take a simple one, just an add immediate. Add 1 to the value in register X3 and put that in register X4. So if we only wanted a semantics for some very specific use, for example, for a compiler verification project, then we might think that the semantics of this was a function that takes the state and adds 1 to the register value in X3 and puts that in X4. And we could write that down in a couple of lines. And indeed, this is the Concert 3.6 semantics for an add immediate ARM instruction. And you can see that is exactly what it does. It just adds 1 to some value from this register state and puts the result into that register in that register state. If we look at the real thing, there's quite a bit more going on. Right? So this is actually a whole family of add instructions and actually a whole family of add and subtract instructions. And there's, if we look at the real definition, so this is the sale translated from the ARM definition, then there's some decode pattern matching, really decoding the bit vector. And that's also got some kind of exception mechanism in it, unfortunately. There's a bit more decode. So this is now matching some of those bit fields in the upper end and turning them into semantically meaningful things. So 0 extending and such like. Sorry, here is the exception mechanism. Then we call another function add subimmediate, which does real computation. Right? And you can see, well, this is both add and subtract. So if it's a subtract, then it will negate one of the arguments, and then it will futz with the carry bits, and then it will, if the set flags field is set, then it will set some flags and so on. And then there's a bit more complication because some of these registers are actually banked, and which stack pointer you get depends on the exception level. So there's some more auxiliary functions to deal with that. And then at the very bottom, finally, we get to a function that actually computes values of flags and the result and so on. So there's a lot of stuff which if you want to reason about instructions in full generality, you have to deal with. But in some cases, it may not matter. There's a lot of detail, but it's quite simple, conceptually simple stuff. Lots of bit vector manipulation, which is why we need this dependent type bit vector stuff. I'll skip over that, skip over that, skip over that. So what about the prover definitions that we generate from these? Are these disgustingly terrible or are they usable? So they're kind of straightforward. So there's a monadic translation with one mono or another of the register and local variable effects and these sale exceptions and non-determinism. There's not much non-determinism in the sequential aspects of the ISA spec. And then there's this bit vector dependent typing. So for translating into cock, we retain that from the source sale. For Isabel and Hol 4, we monomorphize as much as necessary, but no more than that in order to keep kind of usable definitions. So I'm not going to walk through these, but just to let you eyeball them for a second. So here's the Isabel of one of those pages. And see, it looks a lot, that has the same structure as the source, has the same names as the source. It's not too terrible. And you see a bunch of monadic bind operations scattered around. And the cock version is basically the same thing, right? In this case, a little bit of subtlety up here. So these are mostly produced by Thomas Bauerreis and Brian Campbell, respectively. And this is automatic, so each time we receive a new version of the ARM spec from them, we can regenerate all of this. But there is all that complexity, and sometimes it's just too much. Sometimes you have a particular instruction in your hand and you want to know what it does. So now this is a new thing. This is actually not published yet. This is a sneak preview that I'm giving you here. This is work by Alistair Armstrong, who's now the main developer of Sail. So he's produced a symbolic evaluation tool, ILA, which can simplify that full instruction semantics. So if we know we've got this concrete opcode of this assembly instruction in our hands, it can simplify all of that stuff down to something which is basically what you would like to see: a register read, an SMT formula describing an addition of 1, and a register write. Actually, in the real thing, there are 2 more lines which I've optimized away. So this gives us kind of the best of both worlds. We get a authoritative semantics, but for specific code, we can simplify it down to something usable. We have to trust the tool, I have to say, so ILA itself is not verified. Okay, so that's the sequential ISA. Maybe, do we have any questions yet? We do not so far have questions, but I encourage you once again.
Yeah, so there are 2 questions. One is,
sorry, I don't see them in my Clouder, but
I can read them.
Yeah.
So it has several delays. So Sophie Touré asks on slide 21, what fails?
Slide 21, what fails? I don't even remember. I think they might have been some corner case in floating point, maybe? I'm sorry, I don't remember. I should note also, so as not to mislead, it's not the case that the ARM model passes all of these tests either. So, you know, total certainty is nowhere to be found, and one should not expect it, which does inform all subsequent verification projects, right? You don't need to be certain. You need to be more certain than this. The second question.
All right. And Simon Gay asks, 99.85% of tests passed a good score. What can we compare it to?
So this is comparing against the ARM internal model. So this is really testing that our translation is good. This architecture validation suite is one of the things that ARM provide to their architecture partners to test that, for example, let's say a Qualcomm designed silicon is an ARM.
So I mean, what I meant was, you know, 99.85% sounds extremely good. But then if you look at the telecoms industry, they're going for 6 nines reliability. So how do I know whether 99.85% is something to be impressed by or not?
I would advise you to be quite impressed. How do you know for sure? So that validation suite is not a public thing. So it's, you know, part of ARM's core IP. So you can't, I'm afraid, assess by reading that. But you know, this is one of the things which is a major component of the validation applied to new silicon. So we are certainly sort of playing in that game, we could not say that this is as well validated as new silicon.
Okay.
Does that answer the question?
Thanks.
Yeah. All right. So it's probably a better experience if people unmute themselves and ask the question. So Freak, do you want? There's a third question from Freak. Freak, do you want to ask a question? The question live?
If you like. So I wondered about underspecification. So I know C, and there you have something called undefined behavior. I wondered whether these systems also had some underspecification, like some bits that it's not specified what will be the state after an instruction, and how you handle that in your cell model.
So it's, we could talk for a long time about that topic. Maybe we should mostly do it offline, but just quickly. So there can be nothing of the nature of C undefined behavior in a processor spec for a production processor, because let us say you have a system with a hypervisor. The system as a whole has to have well-defined behavior, even in the presence of arbitrary malicious behavior by some guest. So
I shouldn't have mentioned undefined behavior, but is it underspecified? Let's say.
So there's certainly some loose specification. So obviously in the concurrency semantics, there's any amount of non-determinism. In the ISA semantics, there are some places, not all that many, but a few, where one has an unspecified value, an unconstrained value. And there are certainly some places where one has what ARM describe as constrained unpredictable behavior. Now in the ARM text, that informally means you might get any resulting state that could be obtained by a sequence of instructions at this exception level. And nailing that down is a thing that is sort of on our to-do list together with ARM, but is not yet done.
Okay, thank you.
So for many verification purposes, you would actually want the model in such a case to just raise a flag and announce that you have reached such a state, rather than reason explicitly about all of those subsequent states. And that is the semantics that we currently have. Okay, so that was sequential stuff. So I'm not in this talk going to talk really in any detail about the concurrent world, because that would need another several hours of talk. And the time zones are not big enough. But let me just mention very quickly. So in the concurrent world, for any of these high performance architectures, there are many hardware optimizations which can have programmer visible effects. And in the last 10 years, we and other colleagues and ARM and IBM colleagues and so on have worked to nail some of this down. And for user mode concurrency, it's now in a pretty good state. So we have models in several styles. So axiomatic models, predicates on complete executions, and this is what you'll find in the ARM manual. We have operational models that have some microarchitectural flavor, which is good if you want to understand why things behave the way they do. But it adds some complexity, which is bad, but it gives you models which you can incrementally execute, which is good. And then we have these operational models in a promising ARM style by Poulter and Gil Herr's group and Jean-Pierre Faribault. And these are more abstract than these. They don't have that that microarchitectural nature, but you can still incrementally execute them. And there are proofs of the equivalence between these. So this is a very nice situation to be in for user mode code. And then we have tools, or the world has tools that can work over them. So previously, for many years, Jad Algarve and Luc Méranger have been producing this herd tool for axiomatic models, and the Cambridge and St Andrews folk have been producing this RMM operational tool, a thing which is new, built on this SAIL instruction semantics. And again, I'm giving you a sneak preview, is something called Euler Axiomatic by Alistair Armstrong. And this, for the first time, lets us integrate a full ISA semantics with a real concurrency model, in this case, the axiomatic concurrency model. So that means you can take like maybe a litmus test, a little program with concurrent threads, but a litmus test that might involve any instruction from the sequential part of the ISA, and you can plug in an axiomatic model in a fragment of the cat language of herd, and it will do, using symbolic evaluation and SMT solvers, it will evaluate all of the architecturally allowed concurrent executions and show you them, like this one in this picture for this little message passing test. So it's got a spiffy web interface. There's a URL. You can go and try it. Please do. This is all for user concurrency, and that's been the research focus of many people for the last quite a few years. Now, we and others are starting to look at systems features. So what happens when you have self-modifying code in a JIT, or exceptions and interrupts, or address translation and TLB maintenance? And for the first of these, Ben Simner and others had a paper in ESOP last year, which is also now supported by that ILA axiomatic tooling. So you can try, I don't want to talk about the details of this test, but it's a test with self-modifying code and instruction synchronization barriers, and the candidate axiomatic model for that, produced in some detailed consultation with ARM. So now you can see what's allowed and what's not for such tests. Okay, let me move on to Cherry. So what I've talked about so far is all specifying the architectures that exist today. But the architectures that exist today, or more broadly, the computers that exist today, as we know, they are terrible. Right? So we have these legacy design choices dating back to the 70s of systems languages that don't enforce protection, and hardware that lets you enforce only very coarse-grained protection using virtual memory. And these things are baked in to the critical systems code base. They're baked into the entire industry. Right? It's very, very hard to change this kind of stuff. And the result is that in the adversarial environment that we have today and we didn't have in the 1970s, that pretty much any programming error might lead to an exploitable vulnerability, and 50%, that's probably an underestimate. There's data from Microsoft and Google that says this is maybe more like 60 or +%. Many security problems require a memory safety violation somewhere within them. So why, if we just look at a bit more detail, why is this for real? So here's a tiny piece of C code. There's a secret key. Well, it was supposed to be a secret key. And there's some code which, when you look at it, shouldn't be able to access that key in any way whatsoever. What happens? Well, semantically, it allocates two things, for X and for secret key. And then it constructs a pointer to X. And then it adds one to that pointer. And in some implementations, in some executions, these two things might happen to be allocated adjacently. And this is now the numeric address of the secret key. And if you run this in practice, sometimes it will leak the secret. And is that allowed in C? Well, yes and no, right? The C standard kind of says that this program has undefined behavior, which means it doesn't constrain C implementations, which means it's the programmer's responsibility not to do this. Right? Actually, to make that precise, we need to be able to tell that this pointer doesn't point to the allocation that it was supposed to. And that needs some notion of provenance, which is actually something which Kevin Mamarian and Jens Gusteit and Martin Wecker and I are pushing through a technical specification to make clear in the C standard, because it has not been clear for the last few years. These pictures, by the way, come from Kevin Mamarian's Cerberus C semantics tool, which also has a web interface you can find and use. But, okay, that's pretty useless. I mean, that defines a C semantics, which matches current practice, but it permits these leaks. if we want to do better, we need to change things, but we need to change things in a way which one can realistically get adopted. So Cherry is a project that was started maybe 10 years ago now by Robert Watson, Simon Moore, Peter Neumann, and I came along a few years later. Cherry is a project to define architecture extensions that support hardware-enforced fine-grained memory protection or secure encapsulation, or both, using, instead of integer pointers, using unforgeable capabilities. So let me give you a little bit of an introduction to this, but very quickly, because we're already going slow. So the basic idea then is that where, like for a C program, in a normal implementation, this pointer value would just be a machine word, maybe these days with some pointer authentication or something stuck on, but still basically a machine word. In Cherry, where this thing will give you maybe an exploit, in Cherry, the representation of that pointer is not a 64-bit machine word, but a 128 plus 1-bit thing that contains in some compressed format both the address and the base and bounds of that original allocation that the essentially C provenance semantics is talking about. And also a 1-bit tag that the hardware ensures tells you whether this is a valid, well-constructed capability or not, so they can't be forged. So because you have these in your pointer value to hand, the hardware can do a very efficient runtime check and guarantee to trap if you try and do this access. Right? So at a stroke, that rules out a very large class of security problems. There's a lot of design points which are quite important, which I'm not going to go into in much detail. The idea of the design is that code can never grow capabilities. Right? Software is given a universal capability at machine startup, and after that, the operating system and the allocators and the linker and the compiler and so on will be chopping up these capabilities into smaller pieces. Those tags prevent forging, so the hardware takes care of that. And then the design is very flexible. You can use capabilities for all pointers or just when you need to. It coexists pretty nicely with existing C and C++ code, with existing ISAs, with existing virtual memory if you want. It's sort of carefully designed for a smooth uptake path. The initial focus was on spatial memory safety, and that's really what the hardware is sort of natively supporting, but it also supports various approaches to temporal memory safety. I'm just going to skip over those today. They will come at some additional cost, maybe not too bad. So we can use it for roughly two kinds of thing. So either for this fine-grained memory protection or for secure encapsulation of code that may or may not be Cherry aware. So let me talk to each of these. So for the first, so fine-grained memory protection means we're using capabilities instead of machine word pointers throughout some address space to protect from exploitable coding errors. And by this, I mean, we're replacing pointers with capabilities both for the language level pointers, the things which within the C source appear as pointer types to stack and heap allocations and globals and TLS variables and subobjects and so on, but also to language implementation pointers, stack pointers, return addresses, got pointers, PLT entry pointers, and so on. So if you have a piece of nice C code that doesn't do anything too exotic, you can just recompile it and you get safety, considerable spatial safety for all of these. If you have really low-level gnarly C code that does crazy pathological things with pointers, then you have to work a bit harder to adapt the code, but Robert and our System C colleagues have done a lot of that for real substantial bodies of code, including adapting all of FreeBSD, and it doesn't seem to be too bad. The other thing that you can do is use Cherry to constrain interaction between mutually untrusting components. And you could do that at the moment with virtual memory, but it's expensive to do it at a fine grain. So instead, you can use Cherry capabilities and potentially get much better scaling and very low domain crossing costs. So I'm not going to talk about this so much today, just for lack of time. Okay. Academically, so this has been a big project for, well, now the last 10 and a bit years, over multiple DARPA programs with EPSRC funding, Innovate UK funding, Google, DeepMind, ARM, HP Enterprise. It's a big thing. And it's really unusual and really exciting in that it has spanned hardware implementation. This is especially Simon Moore's part of the project, and the software stack, which is sort of a Robert Watson part, and architecture design, which is both of them, and formal semantics, which is where my group come in. So we've been able to do over the last several years hardware, software, semantics co-design with all of these moving along kind of in sync, and that's been extremely instructive. So on the semantic side, for the last several years, 5 or more, the Cherry ISA extensions have been defined in a formal language. So initially L3 and now the SAIL that I was talking about later. And this use of the semantics as a central design document has meant that the Cherry systems and hardware researchers and engineers have really owned that. Right? We haven't been writing it. They have been writing it. That is success in a sense. So it's used in lightweight ways just as documentation. It's used as a test oracle using the SAIL or L3 ability to auto-generate an emulator, and that's invaluable for testing hardware and for software bring up. And that also fits in with the existing engineering practice that people are used to. Right? Whereas full verification is a much trickier thing to mesh with that. And Brian Campbell has been using it, also exploiting this ILA tooling for automatic test generation. And we've also used the SMT property checking. So these are all sort of lightweight things, so not full verification, but exceedingly useful. For full verification, well, here's this architecture spec. How do we know that it does enforce the intended security properties? And indeed, what even are those properties has not been all that clear some of this time. So what we've done for this is use our SAIL infrastructure to generate theorem prover definitions above which we can state and prove that specific security properties do always hold. So what kind of properties? So I'll just give you an idea. So these are a couple of properties from Kinderland Nienhaus's paper from Security and Privacy last year. So for any intra-domain trace, so if you start the machine or if you have the machine in any state, you have the architecture in any state, and you watch it execute for some trace up to the point of some domain crossing. So say up to the point of a hypervisor exception or something. The reachable capabilities in the final state are no greater than those of the initial state. So this is the fundamental capability, reachable capability monotonicity property that the architecture aims to give. And then a property about encapsulation. Any trace within a properly set up compartment, and the devil is in the detail of exactly what that precondition is, cannot affect other memory and can exit the compartment only in some controlled ways. So these are proofs, mechanized proofs in Isabelle, adapted as the ISA has evolved. So not sort of once-off things, but things we've been able to redo and keep up to date. They are properties of the architecture. So we're not proving that the hardware is correct, and these are not properties about software. They're purely properties about the architecture, but exceedingly valuable for that. Okay. So this is all good and all, and that sounds like a cool academic project, right? Well, I would think so. But is it actually adoptable? So there's academic evaluation about how much effort it is to port software. evaluation about performance. That's always tricky to get numbers that are meaningful. But very encouraging evaluation academically, and that makes ARM and several other major vendors very interested and involved in this. But it's not so far been evaluated in a modern high-end superscalar core on a large corpus of industry software. And that means even though Cherry is carefully designed to not be a big shift from normal practice, it's still hard to get commitment to switch to it without a demonstrator on a modern high-end superscalar core. But it's quite expensive to build a modern high-end superscalar core, and therefore hard to get that investment without industrial commitment. So this is has been an annoying chicken and egg problem for the last couple of years. Fortunately, being resolved even as we speak. So a couple of years ago, we saw an opportunity in what the UK has an Industrial Strategy Challenge Fund, which hands out money to not very many, but rather more substantial projects than usual, aimed not at academic research, but at really supporting industry to do things that it cannot otherwise do. So we saw the opportunity for Cherry to fit into that space, and slightly to our surprise, so we applied and we thought probably nothing would come of it, and then to our continued surprise, it was funded. So this Digital Security by Design is a UK government funded program, well, 70 million from the UK government and 100 and something million of industrial match funding. And the idea of this is that it is building a Cherry ARM prototype. So this is called Morello, and it's a prototype architecture and hardware implementation and SoC and demonstrator board and software and some proofs. Right? So the idea is that this will get us out of that chicken and egg problem. It will let people, both ARM and also other vendors and also academics, validate that these concepts really work and are practically viable at scale. Right? And there is actually emulation models already available. And this board, if I remember the schedule, which I might not, the actual physical board will be available sometime either later this year or very early next year. It won't be available in vast numbers. They're only making, maybe less than 1,000 of them, but enough, because it's not intended to be a project, but enough to support real evaluation. So here's a slide from ARM. It's very unusual for ARM to do this kind of thing, to produce an experimental prototype, and what is in Morello is not guaranteed to be in future ARM, future mainline ARM, but the idea is, if it's successful, then the concepts will be carried forward. Binary compatibility will not be carried forward. So it's a high-end processor. It's based on the Neoverse N1 core, built in a 7nm process. It's got a GPU. It's got glue for talking to an FPGA, and so on. It will be able to run Android and such like. And then on the software side, so there are two software stacks in development. So the most substantial one, well, the most substantially developed one is being produced mostly in Cambridge and is an adaptation of FreeBSD to Cherry across the kernel and user space and so on. And then with hypervisors and Clang and LLVM and a variety of substantial applications above it. And then there's also going to be work on Android. We'll see how substantial that is later. Then what about the verification side? So I said the ARM ISA spec was about 100,000 lines long. And if we're adding a feature which is intended to provide some security guarantees, then ARM and we would very much like to have some assurance that at least the architecture does have those guarantees. Right? So we, which is principally Thomas Bauerreis, now also Thomas Sewell, Alistair Armstrong and Brian Campbell, have been doing similar kinds of work as we did for the earlier academic Cherry prototypes, but for this full-scale industry Morello spec. Right? So this is giving us machine-checked proofs of security properties of a full-scale industry architecture for essentially the first time. And hopefully this will then turn into an architecture which is, in a few years, deployed maybe in all of your phones. So this is one potential transition path for Cherry. There are also others. So there's a lot of work on Cherry RISC-V going on at the moment in Cambridge and SRI International. And there's also been work within ARM on an extension to the microcontroller architecture. And there's an IP agreement with ARM that ensures that the basic ideas are actually free to use. Right? So one can perfectly well imagine a Cherry x86 further in the future. Lots of exciting future research, any amount of hardware and software and verification to be done. I think I should, quite soon I should wind up. So if you want to know more, here are some links to a small selection of the many papers available on all these things. And let me go back to the beginning. Right? So is it practical to underpin the foundations? Well, up to a point, yes. Right? So it's very difficult to make radical changes, but we can interpose, even for the existing architecture designs and languages, we can interpose a layer of reasonably trustworthy mathematics. And above that, well, that gives us a foundation that, even though we don't have, it's not guaranteed to be perfect in all respects, but it gives us enough confidence to do really high quality verification above that. And we can push the building back up just a tiny little bit. Actually, the tower, it cost them a lot of money to stop it falling over, and they didn't do it by injecting concrete underneath. They took it by taking out just very carefully small amounts of the crap that was underneath at the beginning, as Ian Stark reminds me. But it's now good to stay, you know. It's going to stay upright for a while. We're in a maybe a slightly better world, which is not something one can say very often these days. With that, let me end and let me answer any further questions.
All right, thank you very much, Peter. Just a reminder to everyone, when you ask your questions on Clouder, please add your name because Clouder doesn't show the name. So we have a question from John Grossen. John, do you want to ask it live?
Sure. So I was wondering whether there are any sail models that attempt to model micro-architectural details, that especially those that are relevant for side channel attacks. I mean, the classic example being Spectre, but related things as well.
So it's an interesting question, and the answer is essentially no on purpose. So all of these, let me just go back. So all of these models, they really are architecture only. And if you want to reason about, if you want to formally reason with confidence about, you know, all the side channels in let's say an ARM implementation of ARM v8a, then you really need an awful lot of detail about the microarchitecture to do that, and that is both overwhelming and proprietary. So for like an A-class processor design, I think doing that is not within academic scope at present. And it would not be, so that detail, you can imagine adding some very coarse abstraction of the potential for side channels to a sail model directly, but to really get confidence, you need to reason about the actual RTL implementation. And that's quite tough for that. For RISC-V, it's maybe more doable, but again, you would have to focus on a specific RISC-V implementation. There is, so I say all of this, but in the operational concurrency models, there is explicit speculation. So you can see if I just step to, like in our operational model, so this is this ARM tool and its web interface, actually you see here a state in which, well, you don't see here, no, I lie. You would, if I had chosen a different execution, see here a state in which this read was being satisfied out of order and possibly speculatively. So to get the observable concurrency behavior right, we had to model explicitly some speculation, but that is not guaranteed to be an exact characterization of the microarchitectural speculation. It's only what you need of that in order to get the observable non-side channel architecture behavior right. So it can be a useful thing to think about, but it's not a guarantee.
All right.
And now I can see Clouder questions for my very own self.
All right. So the next one, or do you want to take them, Peter?
Maybe it's still better for people to ask them out loud.
Right. So Freik, you have another question?
Yes, sorry for asking too many questions. Of course, there's always a cost. So you get reliability, or at least you will know when something bad happens. But do you have any indication how much battery life it will cost, how much bigger my memory needs to be to fit things in? If my codec for my video, do I need to wait longer for a video to encode, stuff like this? Do you have any experimental data?
So there is some data, but it's data from Cherry MIPS Cherry RISC-V, and the extent to which it applies to something like Morello is quite debatable. So I don't want to sort of quote any definite numbers. For a lot of code, it looks as if the performance cost may be almost in the noise, in the small numbers of percents, but it's certainly possible to have code because the pointer size is larger, for which Cherry is not good, and then it'll be worse. I mean, I think if the cost was, if our, how shall I say this? So we have shared the data that we have with ARM and discussed that in quite some detail, especially on Robert and Simon's side. And I think if it looked as if the cost was going to be very large, then they would not be building Morello right now. But to have confidence, we have to actually build it and test it.
Thank you.
All right. And another question from Ralph Jung. Ralph, you want to ask it?
Sure. Yeah. Hi. Thanks, Peter, for the very nice talk. I was wondering, you mentioned 125,000 lines of SAIL specification, and you mentioned that SAIL is a first-order imperative language. So this begs the question: how much of that 125,000 lines is repetition or patterns that could be abstracted away if you had used, say, a higher order specification language that can provide more powerful abstractions than first-order languages can?
I'm not sure that higher order would actually help you much. So there is within that spec already quite a lot of parameterization. So for example, I showed you pseudocode for the add and sub group of instructions. And that's the way that ARM have it designed at the moment. And in general, one has an interesting choice in ISA specification design of how much of that kind of collapse one can do. So for example, in one of Anthony Fox's ARM models that he wrote by hand a few years ago, he did that very aggressively, and that makes the model smaller, but it also can make it harder to understand. So there's a trade-off there. There is some duplication because of the handling of system registers, of which there are quite a lot. I mean, 1,000 pages of the ARM are devoted to describing system registers and their behavior. And that material in the ASL and SAIL spec is automatically generated by some infrastructure that ARM have from some other format. So there is some repetition due to that. I don't, off the top of my head, I'm afraid I don't know how much. Yeah, on the whole, apart from that, my general sense is that while if one was writing it from scratch, it might be cleaner. I don't think it would be that much smaller, apart from the system register stuff.
Okay, thanks.
Okay.
All right. So maybe I can ask a very quick question. So how nice is nice C code? How nice does it have to be? And what does it take to turn C code into nice C code?
So maybe it's easier to enumerate the nasty things. So if you do, if your C code does cast from pointers to integers and then some elaborate arithmetic and then casts back, which you might do in a low-level allocator or a JIT, then you might have to rephrase some of those things a bit or change some of the types. So for example, instead of, so you still have int pointer t, but now you have the integer type which is big enough to store a capability. If the code used unsigned long for in places where you might now think it should have used int pointer t, then those might have to be fixed up. So there's a thing you can turn on and off in Cherry C, which is whether if you take a pointer to a struct, if you have a pointer to a struct and take a pointer constructed from that to one member of the struct, whether you narrow the bounds or not. If you turn that on, which you may want to do to getting better security, then Cherry will not let you use the container of idiom on pointers to those types. So there's an extra annotation in Cherry C as part of Alex Richardson's dissertation that adds annotations to let the programmer say, on the whole, I want you to do sub-object bounds protection, but for this type, please turn that off because I know I need to do container of. So it's a question mostly of, in some sense, just of cleaning up the code. So code which will work on Cherry will generally also be cleaner code upstream, and then of adding some of these specific annotations.
I see. Is there any automation available for this cleaning process, or is it a process to be done?
I would have to check with Alex.
I think washing machine.
I mean, there is a reasonably engineered Clang and LVM compiler that gives errors and warnings. I think that's roughly the state of the art.
All right, thank you very much.
Mm-hmm.
So unless my clouder,
I think we need to move to
right. So I think we started 10 minutes later, so I think we are good. So thank you very much again, Peter. And something that we haven't told you before, but there is a breakout room where people can ask more questions. So I think there were some questions that were calling for follow-ups, and there was this reference to providing more details. So I have created a breakout rooms where people can join. So you, Peter, and any participant can join and ask more questions. So if you click on more and breakout rooms, you see room 1.
It's not yet created. I think you needed to open them or something. There is okay, now it is.
Right. Thanks. Now it is created. So please, if you have more questions for Peter, join the breakout room.
Okay. Thank you, and thank you all.
Thank you.
Thank you very much again. So I think we can now proceed with the next session. We have William, the session chair.
Hello.
Hi, William. Please, you have the floor.
All right. Yes. So our first regular session of talks here today is titled Program Logics, although it might as well be titled Separation Logics or indeed just Iris. We're going to have a couple of talks about neat techniques for proving correctness of programs with concurrent separation logic. To begin with, a new approach to proving correctness of the Michael-Scott queue. Simon?
Hello, my name is Simon, and I'll present the paper Contextual Refinement of the Michael-Scott queue by myself and Lars Birgedal. In this paper, we prove that an implementation of the well-known Michael-Scott queue is a contextual refinement of a coarse-grained queue. These queues are implemented in heaplang, a language with higher-order functions, higher-order store, universal types, fork-based concurrency, and other challenging features. Proving contextual refinement in such a language is notoriously difficult, and we therefore use RELOC, a logic for proving contextual refinement, which offers high-level rules that greatly simplifies such proofs. RELOC is built on top of Iris, a higher-order concurrent separation logic framework, and this means that RELOC inherits a lot of the features found in Iris. All of our results are formalized in COG by using the COG mechanization of RELOC and Iris, and the Iris proof mode for interactive development of proofs. Additionally, the generally applicable constructions that we develop as part of our proof, namely the persistent points to predicate and the resource algebra of discardable fractions, which I'll explain later, have been upstreamed into Iris, which means that they're now available for all Iris users. To understand our main result, I'll give a high-level explanation of the Michael-Scott queue, the coarse-grained queue, and the definition of contextual refinement. The Michael-Scott queue consists of a linked list with the values in the queue stored in the nodes. The first node is called the sentinel, and the value in this node is not a part of the queue. The queue maintains two pointers, one called the sentinel pointer, which always points to the sentinel, and one called the tail pointer, which points to the tail node. The tail node is either, as in this diagram, the last node, or, as in this diagram, the second to last node. And in this case, we say that the tail pointer is lagging. Okay, so let's now look at the two operations, DQ and NQ. DQ proceeds by reading the sentinel pointer and the sentinel's successor. Then by using compare and set, or CAS, it attempts to swing the sentinel pointer forward such that it points to ln. And if this CAS is successful, the value in the node is returned. If it's not successful, then DQ restarts. NQ allocates a new node with the value that is to be NQ'd. It then reads the tail pointer and uses CAS to try and change the successor of this node from pointing to a nil node into pointing to the new node. If this is successful, the tail pointer is now lagging behind, which by the way is exactly the reason why the tail pointer is allowed to lag behind. And to make the tail pointer point to the last node again, NQ attempts to swing it forward with a second CAS instruction. Okay, so the entire implementation is as seen here, and it's a bit more complicated than what I've described, but we don't need to understand all the details for this talk. So let's now consider the coarse-grained concurrent queue. The details here are also not that important, but the key thing to understand is that it is implemented using a reference to a functional list and a lock. Both NQ and DQ acquires the lock, and thereby they have exclusive access to the list. DQ removes an element from the list, and NQ adds one at the end. So this is, loosely speaking, the simplest possible way to implement a concurrent queue, and we can reasonably consider this to be obviously correct. The contextual refinement that we show then implies that the Michael-Scott queue is as correct as the coarse-grained queue, and if you're willing to accept that the coarse-grained queue is correct, then the Michael-Scott queue is as well. The definition states that an expression E is a contextual refinement of E2 if for any context K, whenever K with E1 evaluates to a value V, then K with E2 can evaluate to V as well. And in this definition, we think of E1 as the implementation, in our case the Michael-Scott queue, E2 as the specification, in our case the coarse-grained queue, and K as an arbitrary client that uses a queue. So the refinement that we show means that in any program, one can replace uses of the simple, obviously correct queue with the Michael-Scott queue without changing the behavior of the program in any observable way. Okay, so in the paper, we identify and explain the following step-by-step approach to proving contextual refinement with RELOC. And by far the most difficult step and most interesting step is the third one here, where one has to come up with a suitable invariant. This invariant is used to prove that the operations of the Michael-Scott queue refines their coarse-grained counterparts, and it must be preserved during symbolic execution of the operations. To this end, the invariant must do two things. First of all, to show that the operations are related, we must show that they evaluate to the same values. And therefore, the invariant must relate the state of the Michael-Scott queue to the state of the coarse-grained queue, ensuring that they contain the same values. However, that is not enough. Operations on a concurrent data structure typically makes certain assumptions about what other threads may do. So we can say that they adhere to a certain protocol, and their correctness rely on the fact that other threads respect the protocol, and they in turn must respect the protocol themselves. To understand what the protocol for the Michael-Scott queue could say, let's look at the MS queue again. First of all, recall how DQ and NQ changed the sentinel and tail pointer. They both did this by advancing the pointer to a succeeding node. Hence, the first requirement could be that the tail and the sentinel pointer are only swung forward. Secondly, while the tail pointer may lag behind, it's not allowed to lag behind the sentinel pointer in the case where the queue is empty, as seen here, i.e. this situation is not allowed. Thirdly, the only way to mutate the linked list should be to insert a new element at the end, which is what NQ does. Changing the list in any other way should not be allowed. And the key idea in our proof is that we can encode all of these aspects of the protocol by using 1, a persistent points to predicate, and 2, a notion of reachability. Let's first look at the persistent points to predicate. So in order to encode that the nodes can only be appended at the end, we introduce this persistent points to predicate. And it reads L always points to V. We use the persistent points to predicate to represent all locations in the single linked list, except for the one location leading to the last nil node in the end. And this ensures that the list can only be mutated at the end when a new node is inserted. Okay, so in Iris, the points to predicate is not a primitive of the logic, but defined using what is called the Iris base logic. So to introduce the persistent points to predicate, we can redefine and generalize the existing points to predicate inside the logic. So whereas the existing points to predicate in Iris is the well-known fractional points to predicate, we generalize this to a points to predicate parameterized by what we call a discardable fraction. So instead of a fraction, we have a discardable fraction. And the discardable fraction is in turn a generalization of the normal algebra of fractions. So very briefly, elements of the algebra of fractions denote exclusive ownership over some fraction of the whole, and elements of the discardable fractions can then additionally denote the persistent knowledge that some fractions have been discarded. And this knowledge implies that no one can own the entire fraction, and since the entire fraction is required to mutate a location, by owning the points to predicate with the knowledge that a fraction has been discarded, which we denote with this square, then one can know that the location is never changed again. So by generalizing the existing points to predicate in this way, the only new rule that we have to add is the one for introducing a persistent points to predicate. Everything else is just generalizing existing rules. Okay, so now we get to reachability. So as mentioned, we must ensure that the sentinel is always behind the tail. And we enforce this by saying that the tail node should always be reachable from the sentinel, meaning that by traversing from the sentinel, one can reach the tail. And we express this with reachability, which is defined as what one would expect, except for the use of the persistent points to predicate. And with this notion of reachability, we can express that one location can reach another location. But that is not enough, because we also need to enforce this aspect that the sentinel and tail pointer are only swung forward, as mentioned. And if we think about what that entails, then we can say that since the sentinel and tail pointers are only moved forward, whatever node is currently the sentinel or tail at some point in time will be able to reach whatever these nodes are in the future. So if we see a node right now and it's the sentinel, then at some point in the future, whatever is the sentinel at that point in time will be reachable from the sentinel we saw earlier. And by encoding this in the invariant, we can enforce that the sentinel and chain pointer are only advanced. So to this end, we introduce 3 ghost names, which we call abstract nodes, and they give stable names intended to represent this abstract concept of the current sentinel tail and last node at any point in time. And the invariant we use will then use this predicate to tie the abstract nodes to physical nodes. And which physical nodes an abstract node is tied to can only be changed to a node reachable from the one that it is currently tied to, per this rule. Additionally, we then define a persistent abstract reachability predicate, and this denotes that a physical node, Ln, can reach an abstract node, gamma n. And we then have 2 rules that mediate between these, the abstract and the concrete reachability. And one can convert back and forth between these 2, as long as one knows which physical node the abstract node is tied to. And this concludes the talk. Thank you for your attention.
Hi, I am Amin.
Hey, before we move on to the next one, are there any questions? I don't see any in the chat, so I'll start with one. So if I understand correctly, discarding a fraction doesn't just mean that that memory can't be modified, but also that it can't be deallocated. So is there any way that this technique could be extended for a world where we're trying to recollect nodes once they're removed from the data structure?
Yeah, so you're right, there is no way to deallocate allocation once it's been made persistent. And I don't think there is a way to do that. At least I can't think of one.
Okay. Any other questions for Simon?
May I?
Please.
Yeah, so related to persistence points to, so my question is that how much does it, like the abstraction, how much does the abstraction buy you? If instead you know that the structure of the list is unchanged, so you just have some ghost state to store that structure as a persistent fact, and that you have an invariant saying that all of the normal points to have to form following this persistence list.
So I'm not entirely sure that I understand.
So imagine you have an invariant and you say that, oh, this is the, you have a ghost state that store that this is the list, and this list can only grow, it cannot change, like what have been inserted into the list state there, and then you tie all of the points to that.
Yeah, so you can definitely use an invariant where you add some ghost state, and one way or another, that ghost state will also ensure you that the list doesn't change. But if you do that, I think you will just end up with something that's a lot more complicated than what we have here. So I think that this persistent points to predicate will essentially give you a much simpler or cleaner way of expressing that this location never changes.
Okay, yeah.
Any more questions?
Was wondering, could you have a sort of region for managing the allocations, where you, well, instead of using your discardable fractions directly on points to, you could use a discardable fraction in the context of this region, but then have a way to say, okay, but now we deallocated the region, so all this memory is now gone away.
I don't know how you would do that in Iris, but
yeah, I mean, there's not enough context in the question. I agree. Some idea. But...
Yeah, so I think the key problem for deallocation is that once you've made created a persistent points to predicate, basically sort of like everyone knows in theory that this location points to this value. So if at any point you deallocate it, you actually invalidate that knowledge, because now it might be allocated again later and point to something completely different. So I don't see how you can make this idea compatible with deallocating things.
Well, the persistent part would not be alone enough by itself to know that there is a value there. You would need a persistent part plus something else, which you have fractional ownership.
Yeah, okay. And you need both in order to actually read the location. Yes.
So the fractional part would be the region in question, and then you allocate like you have a discarded ownership of something within the region, in a sense.
Yeah, that sounds possible.
Right. We can have time for probably one more question.
I think there is a question in the Clouder chat that's probably not visible because of lag issues.
Herman had a question, yes. Herman Del Bianco.
Yes, sorry, but yeah, I have a question as well as for the discarded fractions, but I think it's related to the allocation later. So my question was whether if the discarded fractions were only required to remember which permissions were owned, whether it could be done with other pieces of ghost state like regular histories or something like that. But I think that we have already been covered that in the subsequent answers.
Yeah.
All right, then thank you all very much. People are interested in continuing the discussion, we can make a breakout room. But for now, let's move on to the next talk. Amin will present a technique for reasoning about monotonicity.
Hi, I am Amin, and I'm going to present our paper on reasoning about monotonicity and separation logic. First of all, let's see why it is important and interesting to reason about monotonicity for program verification. Let's take this very simple program. It creates a counter and then forks a loop that repeatedly increments the counter. It then repeatedly checks that the counter never decreases. It does so by reading the counter twice and crashing if the second read is actually smaller than the first read. Notice that to reason about this program and to prove that this program does not crash, we need to reason about monotonicity. All right, let's see how we do this in separation logic. First, let us look at the specification of the monotone counter. When we create a counter, we get a predicate is counter that tells us that L is a counter and it has a ghost resource associated with the ghost name gamma that is going to track the value of the counter. Initially, we know that the value of the counter is at least 0. Now let's look at the read operation. In the read operation, if we know that before reading, the value of the counter is at least n, then after reading, we get the value m out of the read operation, and we know that the value of the counter is at least m, the value that we just read, and we know that m is greater than or equal to n. All right, let's see how we use our specification to prove that our example does not crash. First of all, at the beginning, we know the value of the counter is at least 0. After reading the counter for the first time, we know that the value of the counter is some m that is greater than or equal to 0. After the second read, now knowing that the value of the counter was m before the second read, we know that the value of the counter is some m prime that is bigger than or equal to m, right? And therefore, this check always succeeds, and we never end up in the crashing branch. Most modern separation logics use partial commutative monoids, or PCMs, to model resources. In this talk, we're going to focus on Iris. A PCM is a very simple structure. It consists of a carrier set, M, which represents elements of the resource,
a binary operation that is partial, commutative, and associative, which represents combining resources, and a unit element that represents the empty resource. Each PCM gives rise to an extension order. We say A is less than B in the extension order if there exists some C such that B is the combination of A and C. A very simple example of a PCM is the monoid of natural numbers with maximum and 0. In this PCM, the extension order coincides with the usual order of natural numbers. Okay, let me say a few words about the predicates that we use to define our specification of the monotone counter. These predicates are defined using the monoid of natural numbers together with the so-called authoritative monoid. See our paper for more details. I will not get into the details of the authoritative PCM in this talk. The important thing is that we define two predicates. One to track the exact value of the counter, and one to track lower bounds of the value of the counter. This is evident in the following rule that says that if we know that the value of the counter is exactly n and know that it is at least m, then m must be less than n. This rule basically follows by basic properties of the authoritative PCM and the fact that the extension order in the PCM of natural numbers actually coincides with the order on natural numbers. The is-counter predicate is simply an invariant that says that the value stored in the counter is n for some natural number n, and that the value that we track in resources for the exact value of the counter is also n. What is important here is that the authoritative PCM allows us to use extension order of the underlying monoid in our reasoning. What we have done in this work is as follows. Given a pre-order relation R, we define a PCM called monotone R. The interesting point is that two elements x and y are related in R if and only if their embedding in the monotone PCM is related by the extension order. This means that we can use the monotone PCM together with the authoritative PCM to reason about monotonicity with respect to any relation R. The construction of the monotone PCM is category theoretically speaking a canonical construction in the sense that it arises as a free functor. And it roughly corresponds to taking the joint semi-lattice completion of R. See our paper for more details. In the paper, we also discuss interesting examples. We discuss construction of monotone references with respect to arbitrary pre-order relation on values. We reason about execution paths in concurrent programs. We show that certain execution paths are impossible. And we use our construction to reason about causal consistency of a distributed database. This approach to reasoning about causal consistency is what we have used in our POPO paper that is going to be presented later this week. Finally, all the results that are presented in the paper and that I just briefly mentioned are all formalized in COC and are available online. Thanks for your attention.
Thank you very much. Do we have any questions? I think that I have not missed any questions from the Clouder. Let me start off. Certainly this is very useful. I've done plenty of separation logic proofs where we needed pre-order-based ghost state. A lot of these can more or less naturally be expressed in terms of state machines, which is also something that's sort of been well established in the ghost state literature. So do you have a good example of something that's more natural to express just as a pre-order rather than writing out a state machine?
Something that is more natural. I'm not sure what you mean.
Just to say, do you have a place where you've used this monotone construction for a pre-order where you wouldn't want to go to the trouble of writing out a state machine ghost state instead?
Yes, okay. Indeed, the third example that I mentioned, reasoning about causal consistency, the relation that we have there is basically a causally closed subset, as I call it. And it's basically a relation between two sets. And it says that set A is a causally closed subset of B if it's a subset of it, and for every element that is in the subset, its causes are also included in the subset. And that is not something that you want to encode as a state machine.
Okay, thank you. We have a question from the Clouder, although I don't know who asked it.
I did. Would you like me to ask the question?
Yes, please. Yeah.
Okay. Yeah. So you mentioned that this essentially free pre-order on a commutative monoid was related to the joint semilattice completion. If it wouldn't take too much time, how exactly are they related? Is it the same as the joint semilattice completion or different somehow?
It is basically a joint semilattice with the bottom element completion. The idea is that if your order is already a joint semilattice, then you can take the join operation as the operation for your PCM and the bottom element as the unit. And everything basically works out. And if you don't have that as structure on your order, then you take the completion, and that's what you get.
Huh. That's pretty nice and simple. And this ends up being the free functor from commutative monoid into preorder?
From commutative monoid to preorder, no. It's
no. Okay.
It's a free functor from. Well, I have to let me bring up the paper just a second.
Okay.
I can maybe.
If the answer is complicated, I can, of course, just look at the paper for details.
Yes, you can look at the paper. We have a diagram there, and you can see the free construction. But okay. It's not on PCMs directly.
Okay. Thank you.
Yeah. Any more questions? Thank you very much. I believe we now have a break before the next session. So we'll see you back again in about 25 minutes.
Yes, and if you want to talk more with Amin, there is still the breakout room. So Amin can go there. And I think we should stop recording and stop live streaming.
All right.
Thank you, William.
My pleasure.